Pleasure to introduce Daniel Elton from Lancaster University. We'll talk about symmetric fields and zero modes for the Weyl-Dirac operator.
Thank you. Thank you for coming along. And well, obviously, thank you for the organizers for the invitation to come down here and get away from the daily distractions for a couple of weeks. And fortunately, I've been able to make a bit more progress on getting this written up so I can actually get it out at some point. Okay, so this talk is sort of in two sections. In the first part, I want to introduce the problem, zero modes of the Weyl-Dirac operator in R3 or in 3 dimensions more generally. And then we'll discuss a few of the results and sort of ideas related to the problem. But then I want to move on to looking at symmetries, looking at particular cases of the operator where there's an extra symmetry, develop this symmetry, and then hopefully come back at the end and say something about zero modes. But the second bit, very much looking at symmetries. Hopefully these have broader applicability, not just to the problem I'm looking at here, but will allow other problems to be discussed as well. Okay, so the Weyl-Dirac operator, it's a first order operator, 2x2 matrix operator. This is the version on R3. I have a lovely green pointer that unfortunately doesn't work here. Just about, but yeah, I can't rely on it. So we've got the magnetic gradient, the usual gradient operator with a magnetic potential attached. This is a magnetic, the vector field in R3. For the most part, I'll be working in the smooth situation. I'm not interested in local regularity issues. And the matrices come in through the Pauli matrices, so the classic 3 Pauli matrices, sigma 1, sigma 2, sigma 3, and that gives the 2x2 nature of the problem. Okay, so this is a familiar enough operator. It acts on 2 component functions, C2 valued functions on R3. And if you take any magnetic potential that's locally reasonably regular, L2, locally L2, for example, you can prove that this is actually an essentially self-adjoint operator if you start on compactly supported smooth functions, for example. It gives a unique self-adjoint closure. So we have a nice self-adjoint operator acting on L2, or C2 valued L2 functions on R3. At some points, I'll also want to discuss similar problems in 2 dimensions. If you want to move down to 2 dimensions, simply forget the third component. So the third Pauli matrix disappears, A3, and the third gradient. Just remove those and you get the 2-dimensional version of the problem.
I'm a bit confused. No, I thought normally when you were defining these Dirac type operators on R3, it was for things into C4. There was.
Yep. So this is the Weyl part of it. This is the sort of geometric. It's half of the.
Okay, so it's really a half, somehow half of that. Yeah.
So this is the somewhat simpler version in 3 dimensions. Okay, so the central question that I'm interested in is whether 0 is actually in the spectrum of this operator, this self-adjoint operator, or in other words, can you find an L2 spinor, L2 C2 valued function on R3 that's in the kernel of this Dirac operator? More generally, it's a problem about the potential as a parameter, which potentials give rise to 0 modes. It's certainly not fully answered. It's quite a subtle phenomenon. Somehow it seems to be it reflects semi-global properties of the magnetic potential, more relevantly the magnetic field that is associated to the potential. It's not a sort of asymptotic properties of the existence of 0 modes in an asymptotic regimes, for example, doesn't depend entirely on what happens to the field locally. It's somehow what the field is doing around loops in R3. So it's quite a subtle problem. Give some sort of results on what's known so far, and then look at what I'm working on at the moment. Okay, well, just a bit of sort of context. These problems arose in several areas of mathematical physics. I'm not going to go into the applications in any detail. Just to mention, or beyond mentioning, the first example, the first construction of magnetic potentials that actually had zero modes arose in connection to mathematical physics. It was a Loss and Yau example from 1986, and this was actually connected to work on stability of matter. So the existence of these things implied there was an upper bound on the coupling constant that would that you could use in their stability of matter results. So there were of relevance there. Other people have constructed examples since then, found applications in other areas. There's also sort of interesting mathematical connections, several. One route to look at, if you want to actually look at the Dirac operator on R3, the Weyl-Dirac operator, you can actually look at the spectrum, and in many cases for the potentials, certainly the ones that we'll be interested in here, the spectrum is the whole of the real line, and it's purely absolutely continuous away from the point 0. So 0 is the only sort of interesting spectral question left. Is 0 an eigenvalue or not? The rest of the spectrum, very well behaved. And this is for a pretty broad class of potentials, some decay properties at infinity, but that's all you really need to get these kind of results about the spectrum being the whole of R. Okay, it's known that the set of zero mode producing potentials is relatively rare or relatively small. So there's a couple of ways that you can quantify this. You can prove, well, the picture to think of is that the set of zero mode potentials inside a broader class of potentials is something like a codimension 1 subset. So the majority, the generic potentials, will not produce zero modes, but if you take a path through the space of potentials you're working on, there's a very good chance you'll trip over potentials that produce zero modes somewhere along that path. So relatively rare, and this can be made quite precise in a couple of different classes. So if you look at L3, potentials in L3, that's certainly true there, but you can also look at other classes of potentials as well. Continuous potentials that decay at infinity at the same rate as L3 would imply. So something like 1 over x, a bit better than 1 over x. And in terms of scaling, if you just take a fixed potential and you scale that, so you start with the 0 potential and scale it all the way up to infinity. So this is taking a line in a straight line, array in your potential space. And you actually look at all the points where you pick up zero modes. First of all, any point where you do, the dimension is finite. The dimension of the kernel is finite. You can get multiplicity with zero modes, but it is finite in these cases. And the total sum you can bound, well, asymptotically order t cubed. So these types of sums, if you just want to count the total number of zero modes, if you scale a potential from 0 up to some fixed t, this will be finite for a very broad class of potentials, certainly all the ones I want to look at. And, well, you can get an algebraic bound on that total number.
Is there also a lower bound?
0. There are examples where you can produce a potential that has no zero modes, no matter how you scale it. So.
And for one that does produce them, do you know that it will keep on producing them as you send t larger and larger, or?
Okay, so I don't have a complete answer. I'm fairly confident that t cubed is wrong. I think the order should be t squared. This is a very rough upper bound. It's somehow picking up complex scalings that produce zero modes as well, which take you out of the self-adjoint realm. So yeah, it's rough. I don't believe it's order correct. In the examples where I can get better results, get concrete results, then yes, you do keep producing them as you go up.
A naive question. Are these zeros the eigenvalue of some other operator that would justify the presence of these zeros?
Well, you can easily turn the zero mode problem around. You can just think of t as a spectral parameter. The scaling parameter as a spectral parameter. And that's essentially where this argument comes from. But this argument will pick up complex scalings that lead to zero modes as well. So if you're only interested in the real ones, that's well, obviously a subset, and it seems to change the order by 1. Yeah, so yeah, you can rephrase it, but it's a non-self-adjoint problem then.
And sorry if so you say you pick up these complex scaling. You were saying some potentials for whatever scaling they might never yield a zero mode. Is that also the case if you include complex scale? Is it the case for any potential that if you complex scale as well?
Okay, I haven't dealt with that directly. Certainly, it's only for real scalings that you don't produce zero modes. And I would believe that, for a complex scaling in general, you will produce zero modes on that order.
Okay.
So if you allow all complex scalings, I think that would probably be the correct order, and there'd probably be some sort of Weyl asymptotic. But I wouldn't want to be held to that.
Yeah, thanks.
Okay, so that's the problem on R3, but this is something that has, well, there's an equivalent version of the problem on three-dimensional manifolds, the geometric version of the problem. You can still talk about zero modes, you can still talk about Weyl-Dirac operators, and it actually pays to sort of move into that geometric context because it helps even with the R3 problem. So there's a sort of a bit of a switch of language. Rather than magnetic potentials as vector fields, we need to think of them as one forms. It's easy enough to move from a vector field to one form. You just put the coefficients in front of the basic coordinate one forms. And then the magnetic field is the exterior derivative of this one form. So it becomes a two form, in particular, an exact two form. So it's just the exterior derivative, but if you want to think about it as curl, then you just take those components of the vector field and stick them in place in front of the appropriate basic two forms. Okay, well that's an easy enough switch. But what makes this problem quite nice, moving to the sort of geometric setting even in R3, is that Dirac operators behave very nicely under conformal transformations. And there's a very nice conformal transformation from R3 to the three-sphere stereographic projection. So that's our pi here. Well, technically you need to include a point at infinity for R3. It's the North Pole if you take standard stereographic projection. But if you have stereographic projection, and we want to introduce the conformal weight, so this is the upsilon there, this is the conformal weight that you get on R3 that makes it look like a sphere. So it's 1 plus x squared, inverse of 1 plus x squared, give or take some constants. So you need to stick the conformal weight around the Dirac operator in a non-symmetric way, upsilon on one side, upsilon minus 2 on the other. And then these pullbacks here are lifting the problem up to S3. And if you do that, what you end up getting is a Dirac operator on S3, and the magnetic potential is just the one that you had on R2 pulled back in the appropriate way using the stereographic projection. So in essence, what we're doing is weighting a Dirac operator with a conformal weight and getting another Dirac operator corresponding to that new metric. So under conformal change of metric, Dirac operators behave very nicely. They just pick up weights on either side, the conformal weight.
Is this actually correct that the weight is not the same power on both?
Yeah.
This, okay.
Yeah, so this thing is going to remain a self-adjoint operator, but on a weighted space. So that's why you need to, well, that's where you can see the weights are going to have to be different on the two sides. So yeah, the Dirac operator on S3 is going to be self-adjoint operator L2 of S3, so C2 valued functions on S3. Okay, well, so what? This is a more complicated setting in some sense, but there is one real beauty of moving to S3. It's a compact manifold. The Dirac operator is elliptic. Elliptic operators on compact manifolds have compact resolvent. They have discrete spectrum. So instead of the zero mode being this embedded eigenvalue in the entirety of the real line, which is all spectrum, is this embedded eigenvalue, we've now got zero. So this makes the problem a lot easier to study. We're studying discrete eigenvalues. We're looking at zero as one of many eigenvalues of the Dirac operator on the sphere, and how does that behave? And it's easy enough to show with this setup here that the Dirac operator in R3 has a zero mode precisely when the corresponding Dirac operator on the sphere has zero as an eigenvalue. It's direct correspondence, no problem with the weights. Okay, so moving to the geometric setting, in particular moving to S3, gives us, in some sense, a much more conceptually easier problem. We're not looking at embedded eigenvalues, we're looking at isolated eigenvalues. Okay, well, if you look at isolated eigenvalues, if you want to think about how they change as you vary the potential, you can start looking at eigenvalue curves. So for example, if we scale a potential, so I'm taking a fixed potential and putting a scaling in front of it, that little t, we get a set of eigenvalue curves for our Dirac operator on S3 that vary with t, and we can start thinking about when they become zero modes, when they cross zero. So you can start looking at things like spectral flow. So that's what I've defined there, the spectral flow, how many eigenvalues cross zero as you scale from zero up to some fixed big T. I'm counting actually positive as the eigenvalues go down and negative as they go up. So you get cancellation. It's just to make the sign convenient for later results. So this is the sign spectral flow. It just counts the total shift in eigenvalues across zero. Positive for those going down, and then subtract off any that go up. You can also look at an unsigned version of the spectral flow. So that actually goes back to what I was looking at before. It's just counting the total number of crossings. Slightly less stable than the signed version, but it's still, well, it gives an upper bound for the signed version. And it's a slightly different quantity measuring something similar. And there's a very nice result for this thing. There's an index theorem, a Tier-Pedodi-Singer index theorem, and you can get a very nice expression for this spectral shift. So the operator you want to look at, so it's actually on a 4-manifold, so you add in a time variable, or the scaling variable, d by dt there, and then subtract off this scaled version of the Dirac operator. That thing is actually elliptic because this operator here, the symbol is essentially purely imaginary, and this one here is Hermitian. So somehow that makes that thing elliptic on this 4-manifold. The 4-manifold is just the parameter range crossed with the 3-manifold. So it's got two ends, but you can get versions of the index theorem for bounded manifolds with boundary. And what you end up getting is a formula that tells you this spectral flow is actually given by, well, this is an integral of a characteristic class on the manifold in some way. And then there's a correction to do with the boundaries. Okay, so this bit here is fairly...
Alpha was the potential?
Sorry.
Alpha is the potential here.
Alpha is the, yeah, it's the one form, the magnetic potential. Yeah. So this object at the end is something called the eta invariant, and it's a regularized measure of how much spectral asymmetry the Dirac operator's got. So you can think of it as the number of positive eigenvalues minus the number of negative eigenvalues, which of course is infinity minus infinity. So it needs to be regularized in a certain way. The upshot is that you get a quantity that can take any real value. It's not restricted to integers anymore. When an eigenvalue crosses zero, the eta index changes, it jumps, as you would expect for an eigenvalue moving from the positive to the negative. But it also varies continuously when eigenvalues are not switching. So it's a bit more complicated than a simple difference of two infinities. There's some regularization in there.
Do you know that you always cross zero with positive derivative? Well, positive with non-zero derivative?
You don't necessarily do that. So for things like the spectral shift function, you need to define it carefully there. You need to perturb it and show that whatever perturbation you take, you'll get the same answer. So yeah, there's some subtleties in how you can define the spectral flow, but no, it's certainly the case that you can have touchings come in and go back out again. Okay, so this looks very nice. We should have a nice result giving us the spectral flow. The only sort of technical issue is that eta invariant is very poorly understood. So actually, although it's a nice formula linking two things, it's linking two poorly understood things, and here we have something that's much easier to get your hands on. This is actually something called the Chern-Simons functional for the potential, or the one form alpha. Okay. So yeah, to look at zero modes, sort of the general problem, there's still lots of open questions. What is possibly something that's slightly easier to have a go at? Well, rather than looking at an individual potential, trying to work out whether it's got zero modes or not, we can try and work with slightly more average quantities, things like these spectral flows or the counting function, the total number of zero modes is n of alpha. And we can look at these quantities in asymptotic regimes in hope of getting at least some sort of results, and this will give some measure of how often zero modes occur. And one asymptotic regime, it's sort of been hinted at quite a bit, is looking at scaling a given potential and looking at scalings that get big. So you can think of this as a strong field regime. You take a fixed magnetic potential or magnetic field and just make it bigger and bigger, scale it up. Now for the zero mode problem, the basic one on R3, if you take the Dirac operator and just divide everything by t, you remove the scale from in front of the potential and just put a 1 over t in front of the gradient. So actually as t gets big, you get a small parameter. It's a semi-classical problem as well. So simultaneously looking at a couple of asymptotic regimes here, semi-classical and strong field. And I have, well, a conjecture for what we actually get in this regime. So if you take any magnetic potential on, well, this M here is sort of switching between S3, R3, depending on which version of the problem you're looking at. So take any one form on S3. The total spectral flow, this is the signed version, up to a parameter t is actually given by that Chern-Simons bit to leading order and some correction, a smaller order correction. So that's what I think is going on here. In other words, this eta invariant is actually bounded by something less than t squared. That's an equivalent way of formulating it in terms of the eta invariant. I believe something similar holds for the actual counting function, not the signed version, but the full counting function. I believe that's also of order t squared rather than the t cubed bound that I had earlier. But it is certainly the case that the coefficient may be different. So here there's a t squared with a coefficient, the Chern-Simons function. I have examples, can compute examples of the actual total number where you have t squared behavior, but the coefficient is somehow like an L1 version of this. You need to put mods inside, so it can actually be strictly larger than the coefficient of the signed spectral flow.
You say this is like based computation for a characteristic class. Does it mean that for alpha in the same cohomology or something like this, it would give the same value?
In the same cohomology, you mean differing by?
No, like
well, if you add on an exact form, that's just a gauge transformation, and then the Chern-Simons function is invariant under that. Yes. Yeah, so I mean the result there is actually, I'll just pop back up, is actually stated for the magnetic potential. One assumes the spectral theory is actually determined by the magnetic field, the exterior derivative of the potential. And indeed, if you do make a gauge transformation of the potential, keep the field fixed but change the potential, then that quantity there is invariant. So it has the right form in that sense, even though it doesn't immediately look like it. Okay, so this is where I'll sort of switch to the second part of the talk. So the conjecture in a general setting for an arbitrary one form, I'm not really sure how to tackle that. I've got some ideas, but certainly a long way to go there. But what I have done is look at particular cases where the potential has some additional symmetry, the operator has some additional symmetry, and you can exploit that symmetry to try and understand the spectral theory of the operator a bit more. So I want to switch tack and look at symmetric situations for these operators. So I'm thinking here of a symmetry in terms of an operator that commutes with our Dirac operator. So this commuting operator somehow is being generated by the symmetry. So the first thing to do is actually go looking for such operators. You want it to be a first order operator. On the other hand, you want it to be simpler than the Dirac operator, which is already first order. So you can think of things like scalar first order operators, gradients in a particular direction. Okay, so I'm looking at an operator Q here. It's just the gradient in the direction of some vector field X, possibly with some zero order correction terms, the Q naught there's zero order. When does that commute? Not just with the Dirac operator, but potentially some conformal version of the Dirac operator. So I put some weights around the Dirac operator there to allow for some conformal change of the metric. And it turns out commuting forces the vector field to be a conformal killing field. So the vector field X actually has to generate a conformal transformation of R3. And that's actually a fairly strong restriction. There's about a 10-dimensional, there is exactly a 10-dimensional set of conformal killing fields for R3. It's not like R2, which has this beautiful infinite collection of conformal transformations. As soon as you get beyond dimension 2, there's rigidity. In dimension 3, it's 10 dimensions. Okay, well, once you've got a conformal killing field, then you can actually create a commuting operator. If you make some choices, the weight that you want to put in is the inverse of the size of your vector field locally. This condition here, this is the interior product of the vector field X with the magnetic field. In terms of vector fields, that's X cross B. It says that the magnetic field should be parallel to X. So the magnetic field should be parallel to the generator of the symmetry. And then the final bit, well, it gives you what that lower order correction is, the Q naught. So there's a bit involving the magnetic potential that just turns the gradient into the magnetic gradient. And then there's an additional term involving the curl of the magnetic, the generating field. That's a geometric term that comes into the operator. But you can set it up so that you have a commuting, you have a Dirac operator that commutes with some first order operator. The restrictions are you need to work with magnetic fields that are parallel to some conformal killing field. Okay, so what examples might be of interest? Well, if there's any fixed point in the vector field X, if you want a magnetic field, well, they're divergence free. If you come into the fixed point, you end up getting a singularity. So if you want nice smooth magnetic fields, you actually want to work with fixed point free conformal killing fields. Now on R3 you can actually have some like translation that moves the fixed point off to infinity. But if you want to work on S3, you're essentially looking at rotations. So rotations on S3 are the types of conformal killing field that I'm interested in. I'm moving over to S3 now because, well, everything in this symmetry section can be done explicitly, all of the formulae, etc. Completely explicit, but they get a little bit messy, and they get messier on R3 compared to S3, where the problem is somehow more natural. So S3 I'm thinking of is unit sphere and R4, coordinates for R4, x1 up to x4. And then there's two basic rotations you can think of for the 3 sphere. These are actually rotations in R4. You can rotate in the first 2 variables. That's what this vector field is doing. It's just a standard rotation of R2. In the first 2 variables, leaves the second 2 alone. And alternatively, you can rotate in the second 2 variables independent of the first 2. So these are orthogonal rotations in R4. Rotate in one 2-dimensional space or rotate in the other. And these are completely independent. And the rotation of S3 they'll want to do is taking a mix of rotating in one plane and the other plane. And I want to allow variation of the parameters. So these kappa 1, kappa 2 are the frequencies of the 2 rotations. And I want to allow possible, well, all possible variations there.
Sorry, you do this to avoid fixed point.
Ultimately, yes. If you have one of these equal to 0, you will pick up fixed points. If they're both non-zero, you don't have any fixed points. It's okay actually to have one of them equal to 0. That's a collection of fixed points. It's not a single fixed point. It's actually a whole circle of fixed points.
So it doesn't matter if the omega will be 1 over 0.
Okay, so in that case, yes, you'll have boundary considerations. It's a slightly different problem. Yeah, the ones I want to talk about here are going to be non-zero for both kappa 1 and kappa 2, but you can push it to one of those being 0, and it's a perfectly sensible problem, but it needs a different setup. So yeah, the basic idea, we've got a commuting operator. We want to reduce our Dirac operator to the eigenspaces of this commuting operator. And what is the Dirac operator going to look like on these eigenspaces of the commuting operator? Well, intuitively, you might expect the Dirac operator to reduce somehow to a Dirac operator on a lower dimensional manifold, onto a 2-dimensional manifold, somehow representing the orbits of the vector field X. I mean, that's sort of intuitively what happens when you have a reduction of order. And that's something that you sort of, it's somewhat helpful to keep in mind here. So we're trying to reduce the Dirac operator. We want to get a new operator that just works on the various eigenspaces of the operator Q. Well, identifying what those eigenspaces are is one thing, and then trying to get an operator that works on those eigenspaces that somehow still looks like a Dirac operator on a lower dimensional manifold. If we can do all that, then hopefully we can say something about these reduced operators and then pull that back up to say something about the spectrum of the whole Dirac operator. Okay, so there's a couple of special cases that have been looked at quite a while back now. One very nice case is if the rotations in the two orthogonal planes are actually have the same frequency. So you do one lap, and at the same time you do a lap in the other direction, and you come back to the starting points at the same time. So this is actually something that's very well known. It's the Hopf vibration of S3. So it reduces everything down to the sphere. The orbit space is then the sphere. Dirac operators on the sphere. Okay, there's a bit of geometry going on there, but they're perfectly well understood. And the information about those can be moved up to get information about the Dirac operator on S3. And this was done by Erdős and Solovay back at the turn of the millennium. So they wrote a paper on that using that basic symmetry of the Dirac operator to get information about zero modes. Another case that you can look at is where one of the parameters is 0. So this is a rotation in one plane only. It's fixed in the other plane. You end up with a whole set of fixed points for your vector field x. And these somehow become a boundary. So the orbit space reduces to something like a disk. Well, you can make it a disk. And then the boundary points on the disk, they need special treatment. So instead of a two-dimensional problem on a nice closed compact manifold, you end up with a two-dimensional problem on a bounded manifold. And then, well, you can introduce appropriate boundary conditions. You can study that problem. And actually, you can show in this situation, you do not get any zero modes. So all the fields parallel in R3, all fields parallel to a rotation about the z-axis, for example. So if you take any magnetic field in R3, that the field lines form circles around the z-axis, doesn't matter how you scale it, that cannot have zero modes. And there's other versions of that. You can rotate around the unit circle in the xy plane, for example. That's the orthogonal rotation in R3. If you take magnetic fields, there's no problem producing such. If they rotate around the unit circle in the xy plane, you can't have zero modes. So there are examples where scaling does not produce zero modes. Okay, so what about the more general case? And this is where I want to restrict our parameters to being positive, well, non-zero, and I'll take both to be positive. What can we say about the orbit space of this vector field x, this one generating our symmetry? Well, if you look at one of the rotations, so say we take V2, this is rotating in the x3, x4 coordinates. So no matter which point you take x3, x4 in the plane, at some point you can rotate it around so it lies on the positive real axis. So you can always rotate it around until you get that component to be some positive number and the 0 in the third component. And that rotation has no impact on x1 and x2. It stays put. So V2 rotates points on the sphere to intersect this set at some stage. And this set is essentially a disk inside the 3-sphere. These two components here are precisely from a disk, the unit disk in C. And then the x4 is just 1 minus the square of the norm of x1, x2 square root, just to make the norm of the whole thing 1. Okay, and V1 does something similar. It rotates points so they pass through another disk. It's going to have x1, 0, and then x3 and x4 are arbitrary. So these individual rotations are not too bad. They can be indexed by points on a disk. The boundary of the disk are the fixed points for those individual rotations. But now we need to combine them. So if we take one of our disks and the corresponding rotation, it rotates points around and they intersect that disk at some stage. But while we're going around that V2 rotation, V1's also playing a role, and that's rotating around the disk. So when we do a lap of V2 and come back to the disk, V1 will have shifted us. So what we end up getting is a shift by 2 pi rho j. Rho j is the ratio of the frequencies. So if you want to think about the orbits being indexed by points on the disk, we then need to start identifying points on the disk that differ by this rotation, 2 pi rho j. So the orbits overall are some sort of quotient of a disk by a rotation of that disk. Now the fun is that that rotation need not be, well, it could be anything. It could be rational or it could be irrational. So we get a very, well, you can already see that the orbit space is going to get a little bit nasty. It's a disk somehow quotiented, well, disquotiented by rotation. And when the rotation is irrational, we get something that's not even going to be Hausdorff. It's quite a messy space. And I want to somehow do something with that space, and I want arguments that don't depend on the rationality of that ratio. I want to try and keep this arbitrary. Any ratio, any pair of frequencies, kappa 1, kappa 2. They don't really, the rationality doesn't appear in the original problem. It shouldn't appear in the answer in some sense. So how can we actually keep all our arguments free of that, that detail? Okay, so what I want to do is give a slightly different description of the orbit space that we can then start doing geometry on. So I want to get an open cover for our sphere. So there's two parts to the open cover. In each part, I remove the fixed points of one of the individual rotations, V1 or V2. So these are two circles. They're non-intersecting circles in S3. S1 and S2 remove one of those circles each. So the version in R3, one of the circles is the z-axis, the other circle is the unit circle on the xy plane, so they don't intersect. Okay, if you take a point in one of these open sets, you can apply our vector field x, and at some point it intersects the disk. Well, it's not just some point, typically it intersects the disk in multiple points.
Could you say what these disks are in the R3 picture with the two?
Okay, so in the R3 picture, one of the disks is the unit disk in the xy plane, bounded by the unit circle. And the other disk, you can take half plane, x1 positive, x2 0, x3 arbitrary. So it's a half plane in that. Yeah. So the integral curves of x will intersect those, either of those disks. If you just focus on one of them, they'll intersect. But as you go around, they'll intersect in many points, infinitely many in the case of irrational rotation. Okay, so first of all, this map uj, it takes the point in Sj and maps it to a set of points in the disk corresponding to all of the intersections of the rotation of the integral curve. So it's a set of points going around a circle inside the disk. Okay, so that thing's not too nice, but what's really nice is that we can then scale our disk. So we've got a disk in the complex plane. I'm just doing a radial scaling up to the whole complex plane, very precisely chosen, so that the resulting map, although multi-valued, is somehow a Riemannian submersion. Okay, so what the hell does that mean? We've got a metric, a conformal metric on our sphere. We need to weight it according to the modulus of x. So they've slightly changed the sphere metric. It's not the usual one. It's this conformal metric. We need to choose a conformal metric on the complex plane. It's some radial weight that you can write down explicitly, although it's not too neat. And then the resulting map. Okay, it's multi-valued, but it's branched. So if you take a particular value and some pre-image, you can have an open set around the pre-image point and an open set around the value, and then the map is just a nice smooth map. There's a branch that is a nice smooth map, and that thing is a Riemannian submersion. So it's the nicest Riemannian map you can have between different dimensions, reducing dimensions. So it's an isometry on the orthogonal. So if you take, so it reduces along the vector field x, but if you take the tangent, the component of the tangent space orthogonal to the vector field x, then this map is an isometry of that tangent space down to the complex plane. So it's the nicest possible Riemannian map you can have, reducing dimensions.
It's like the inverse of Riemannian submersion, because the inverse would be multi-valued. You have a sheeted things.
Well, the inverse is more than sheeted. I mean, it takes a single point onto a whole curve. So yeah, it's sheeted going down. So we take all the points on the integral curve of x and collapse them not quite to a single point, to a collection of points. But if you work locally, it is just a nice smooth map. Okay, and we have a transition between these two. So these you can think of as charts on S3. You can move between S1 and S2. You can project both of those down to the complex plane. Well, you can take them down to the complex plane with this local Riemannian submersion. And then you can switch between the two. If you take the same point that's in both S1 and S2, it goes down to two copies of the complex plane, but the move between them, the transition function, is just a power of z. Okay, so the transition function is necessarily going to be multi-valued as well. You can see that. There's the power there. If that ratio rho 2 is irrational, then it's a very well understood branched function. But it's, yeah, the transition function is just a nice power of z, the constant you can work out explicitly, and so on. So we're thinking of the orbit space now as two copies of the complex plane with points identified according to this transition function. And what that entails is you actually have to identify points within each copy of the complex plane as well as between those two planes. So it's a slightly messy object in a sense. In certain cases, it simplifies a lot. If the ratio, if the frequencies are the same, it's the Hopf vibration, and this construction just gives you the sphere. Okay, and that's nice. We just get the Hopf vibration. If the ratio is a rational number, what you end up getting is something that's an orbifold, something more precisely known as a PQ football. It's got two finite actions at the two poles, and these are given by CP and CQ. And different actions at the two poles. Well, P and Q are not the same. So this is what's known as a PQ football. Okay, so orbifolds have certainly been studied, but if the ratio is irrational, then this thing's not even Hausdorff. It's certainly not part of classical orbifold theory. It's something that somehow goes a bit beyond that. Okay, so that's some sense of an idea. We want to try and do something with this space nevertheless. And what we can do with it, actually, there's an awful lot of structure. Locally things behave. We've got nice branched functions that are all perfectly sensible. And it turns out you can actually do geometry on this set in the way that you would be able to do geometry on S2. You can build up all of the things that you need for Dirac operators. You can put on forms, you can put on line bundles, you can put on spin C bundles, you can do spin C connections, Clifford multiplication, and define Dirac operators. So you can follow exactly the same path, well, almost exactly the same path as you would to develop these ideas for the sphere. You do need to be a little bit mindful. This multi-valuedness is going to come in. We need equivariance conditions to make sure that things are going to be well defined. Whichever branch we take, we get the same object. Okay, unfortunately, all of these constructions...
I'm sorry, just a naive question for the previous slide. How does your set breaks? How do the properties of the sets break when you go from rationals to an irrational number, for example?
Very badly. There's no sort of continuity there at all.
There is no continuity.
Yeah, so I mean, for a rational number, it's still an orbifold. You can still think of it, it's still somewhat two-dimensional in nature. As soon as you hit an irrational value, it sort of breaks down, and really functions then become purely functions of one variable in a sense. So actually, yeah, the switch between those values is pretty horrendous. So trying to keep above that level is, to keep the arguments united is one of the goals of the way I'm trying to work it. Okay, so yeah, unfortunately I'm not aware of any existing work that I can just appeal directly to. I sort of have to go through and repeat all of these constructions and check that the details check out. So for example, if you want to define n-forms, if you want to define an n-form on a manifold, you can take an n-form on each chart and make sure they transition nicely from chart to chart. Well, that's what we do. We take n-forms, theta 1, theta 2, and that's the transition there. You pull back one, you should get the other. Now, tau is multi-valued. We want to make sure it doesn't matter which branch we use to pull back, we want to get the same answer. So the first condition here is what makes that work. If we take one of these n-forms on the complex plane and we rotate the complex plane, we want to get the same n-form. So that's the first condition there. It's an equivariance under rotation, but if we have that, then you can show it doesn't matter which branch of the transition function you use, you'll get the same answer. So this defines a global object on our orbit space, and we call it an n-form. Now, with all of these constructions and the corresponding sort of theory, when we do it on the orbit space, it looks pretty horrendous, and you have to put all these extra conditions in. But in most cases, there's something, a way of interpreting it on R3 or on S3, pull everything back up to 3 dimensions, and there it has a nice interpretation that doesn't reference directly the orbit structure, and it may even be a result. So there's sort of an equivalent way of working, either the sort of classical type looking results on the two-dimensional orbit space, two-dimensional, or move them back out to R3. And this is the case in point. So if you take an n-form on the orbit space, you can pull it back to the three-dimensional manifold. You can do this by pulling back either of the individual forms using the corresponding maps uj. Okay, these uj's are multi-valued, but you can show that it doesn't matter which j you choose or which branch of the uj you choose, you will get the same n-form on the three-dimensional manifold. Okay, so these conditions here are needed to make sure this is a good definition. So we get a nice smooth object on S3 or on R3, and it has some additional properties because of where it's come from. The lead derivative in the direction of x is 0, so as you pull this thing along the vector field x, it doesn't change. Okay, that's no big surprise. We're pulling it back through something that collapses the x's down. And also the interior product with x is 0. So for a two-form, that means the two-form is parallel to x in some sense. Okay, but the converse is also true. If you have any n-form on the three-dimensional manifold that satisfies these two completely sort of standard differential geometric conditions, it arises as a pullback of a two-form or n-form on our orbit space. So there's this equivalence. You get nice conditions on standard objects on N, on R3, S3, or you can view them as standard geometric objects on the orbit space. Okay, the magnetic fields we're interested in, these are two forms on our three-dimensional space. We're interested in two forms that are parallel to X. Okay, there is a basic one that you can always come up with. So remember, we have our X, this is generating our symmetry. We can take the corresponding dual form. So X is a vector field, but if you take the inner product with X, you get a form. Okay, you need to be careful, the inner product is the one weighted with the conformal weight. Okay, so this generates a one form on R3 or on S3. Take the exterior derivative of that, you get a magnetic field. That magnetic field is parallel to X. That's the condition that we want there. Okay, so no matter which one of these conformal Killing fields you choose, you can always generate at least one magnetic field that's parallel to X. So it's a non-empty problem set we're looking at. But actually, if you take any magnetic field on our three-dimensional manifold, so that's the divergence-free condition, the field should satisfy it's closed, and parallel to X. So if we take any such field on R3, then we can write it as a multiple of this basic field that we've got, plus, okay, this is generating a field from a potential, and that potential on the three-dimensional manifold is a pullback of a potential on the two-dimensional manifold. So it's a very precise way of writing the fields that are parallel to X. We're pulling out some multiple of a basic field. This nu here is uniquely determined. And then the remaining part we can think of as something that's arising on the two-dimensional manifold being hauled back up. Okay, so this is actually comes out of Hodge theory for the two-dimensional, the orbit space. So it's not a completely trivial result already. And there's a bit of work that you need to do. You need to develop something parallel to Hodge theory for this. Well, at least that's how I've done it. I'm not sure of any other way to do it, simpler way. Okay, well that's forms. We need to push on a little bit. We need to generalize the idea of functions. A standard way to generalize the idea of functions is with line bundles. So these are somehow functions that have twists as you go around your manifold. And on S2, you already encountered this problem. You can't get away just looking at functions or spinors that are C2 value functions on S2. You do need to think about those that are C2 valued with a twist. So in this case, the line bundles are indexed by this sum of even multiples of kappa 1 and kappa 2. On S2, this would just be an integer, or an even integer, the way I've set it up. Line bundles on S2 are indexed by an integer, the Chern number of the line bundle, if you like. In our situation, the indexing is a bit more complicated. If the ratio is rational, the indexing becomes, well, it's still a discrete set, just there is a lowest common denominator, but it's more frequent than just the integers. But if the ratio is irrational, this becomes a dense set of parameters in R. So the line bundles are now indexed by something a bit more complicated than they would be in standard geometry. Okay, for orbifolds, it's already known that the index can be a rational number. It's sort of just is the next logical step. But what we're doing is simply introducing a phase. So we want to take functions that are defined on the two separate charts, the two copies of C. They need to transition from one chart to the other nicely, and we need the equivariance condition to make sure the multivaluedness of the transition is not going to cause trouble. But now we're introducing an extra phase factor in the two functions. So this E here is just the phase of a complex number, non-zero complex number, Z divided by mod Z, and then E to the K just raised to the power K. So what we want is that these sort of size, these sections of the line bundle, are like functions, but they have an additional phase as we go around the complex plane in a way that matches up nicely. And we can do this for all of these choices of the lambda there. Okay, so this is expanding our class of functions. Okay, these functions, or these sections of the line bundle, I haven't actually defined the line bundle, I've defined sections directly rather than going through the line bundle itself, because that's an object that I can't see how to generalize in such a nice way. But the section is generalized, and we can lift these sections. So if we start with a section of one of these line bundles on the orbit space, we can lift it up to get an honest-to-God smooth function on S3 or R3. We lift it, well, psi j, we can just plug in the corresponding, that's just the lift of psi j there, just plugging in the uj. And then we need a phase correction. So we need to correct by a phase there. This is multi-valued because rho j may not be an integer. This is multi-valued, and to make this definition work, the branch we choose here needs to be correlated with the branch that we choose in there. So that definition is not a particularly nice way of writing it in some sense, because the two choices are not independent. We need to be careful in how we correlate the choices. But it can be done. Okay, so we can lift sections of these line bundles for all the different lambda up to C-valued functions on our manifold. And as I said before, there's, in this case, there's an example where the result on R3, or S3, is actually particularly neat. So if you look at, well, this is the Lie derivative in the direction of x. Think of the gradient. Is nabla, x dot nabla, minus I to make it self-adjoint. This is a perfectly good operator on R3, on S3. If we work with L2 on the manifold has weight, that L2 has a weight, and that weight makes that operator self-adjoint. Well, symmetric to start with, and you can make it self-adjoint by taking an appropriate closure. So it's a self-adjoint operator on M. We can actually now give the spectrum of that operator. It is precisely the set of values of lambda that allow us to give these line bundles. And furthermore, the eigenspace for a given lambda is the lift of all the sections of the line bundle. So the spectral theory of this very simple looking operator on R3 is intimately connected to the geometry of what's happening down on the orbit space. In particular, the line bundles that we've identified somehow are the complete set. They give us all of the spectral information about this gradient upstairs. Okay, so in some sense that's a prototype of the results that I want. I want to lift Dirac operators up to R3. It's going to be a bit more complicated because it's then there's something that's happening with these functions down on the complex plane. Okay, and I don't think I'm going to quite get all that way. Right, I'm going to be a little judicious in what I show. Okay, so to go from where we are, we've got line bundles, but we want Dirac operators. These are not C-valued functions that they act on, but rather two-component functions, spinors, C2-valued functions. So to get the corresponding objects, the functions, the spinors, we need to take a sum of these two of these line bundles. And we need to vary the parameters to make it the neatest form. So the parameter space for this, the spinors, is now odd multiples of the two frequencies, odd multiples of kappa 1 and kappa 2, and then we need to shift those up and down to get even multiples. But then we can take a sum, we get these C2 valued functions or bundles over the orbit space, and we can lift. We can use the lift that we had before to lift each component separately, and we get a lift to C2 valued functions on our 3 manifold. The other thing, well, there's 2 more components to a Dirac operator. We also have the Pauli matrices. So this is something in the geometric setting is called Clifford multiplication. Clifford multiplication you can think of as a map from, so this is spinor valued 1 forms into 1 forms themselves. So a spinor valued 1 form, the simplest version you can think of is just take a 1 form and multiply it by a spinor. And then the Clifford multiplication is take the corresponding Pauli matrix for that 1 form. So the basic 1 forms just become, in R3 at least, they become the basic Pauli matrices. Linearity gives you the Pauli matrix for any 1 form. And then that's 2 by 2 matrix, act on that spinor using the 2 by 2 matrix. So multiply the corresponding matrix against the spinor. That's Clifford multiplication in a nutshell, at least in R3. You can define something similar on our orbit space. And furthermore, it then lifts to a nice Clifford multiplication. If you have the Clifford multiplication on the orbit space and lift the result, you could equally well perform the lift directly and then use a Clifford multiplication on a standard Clifford multiplication on the 3-dimensional manifold. There's an interlacing of Clifford multiplications. Okay, the other component that we need is, well, the generalization of the magnetic gradient. So this is something that's called a spin-C connection. So we can certainly define these as well. This bit here is just the standard magnetic gradient that you would expect to see in 2 dimensions. The D there is the derivative. The other bit is, this bit here is a magnetic potential. And there's a correction. We're in a geometric setting. There is a geometric component as well, but this is fixed. It's independent of the mu and the alpha. Okay, so these spin-C connections do have a component that depends on which spin bundle we're working on. That's the mu. And that's coming in here, mu times this psi. This psi is not quite a 1 form on our orbit space. It's a local 1 form. It generates the constant component of the magnetic field in some sense. And it can't be global because the magnetic field is the exterior derivative. If it was global, then the magnetic field of the exterior derivative would be exact. No, sorry, it would be closed, and, well, be exact. And then its integral, the overall flux, would actually have to be 0, integrating an exact form. So to get something that has a non-zero magnetic field, overall magnetic field on R2, we need these local versions. Okay, well, these connections on our orbit space also lift nicely. If you have a connection acting on a spinor on the orbit space and you lift the result, well, you can just lift the spinor directly and act on it by a connection on our 3 manifold up to a correction. So we can lift to get a spin-C connection upstairs, and then there's an additional 0-order term that needs to be added in order to correct things. And this is, again, geometric. This is to do with the Riemannian submersion. So this, in particular, doesn't depend on the mu or the alpha downstairs. Okay. Right, I'll just go through to the final result. Time a bit quicker than I would have liked. Okay, so as soon as you have Clifford multiplication and a spin-C connection, you can define a Dirac operator. The Dirac, so you take the spin-C connection, that takes a spinor to 1 form valued spinor, and then the Clifford multiplication reduces that back down to a spinor. It multiplies the 2 bits out. If you do that, if you take the composition, this just gives you a Dirac operator. It's a global way of defining a Dirac operator. And you can do this for our orbit space, and the objects you get actually look like Dirac operators would on R2 or on C2. Usual gradient term, the magnetic potential, and we have conformal weights on either side. It's not 1 and -2. In 2 dimensions, it's a half and -3 halves, but it's the same basic idea of conformal transformation. the Dirac operator on n, we can write in a similar way using that composition to for multiplication and the spin-C connection. And now, with everything that's been built up, we have a very straightforward lifting result. If you apply the Dirac operator in the 3 dimensions to a lift of one of these spinners from the orbit space, then that's the same as applying a 2-dimensional Dirac operator to the spinner downstairs up to a correction, which is completely explicit. There's a bit to do with the switch in the magnetic field. Downstairs, the magnetic field is fixed. The total flux is fixed by this mu. Upstairs, the magnetic field can have any total flux you like. That's fixed by the mu. That was the scaling of the basic field. And these things in general differ, and that's to correct for that difference. And this is coming from that curly A on the previous slide. This is the geometric term that comes from the correction that we need to make when we lift one spin-C connection. We get something that's not quite a spin-C correction that filters through. Okay, so this is the spectral reduction that I've been chasing. Don't quite have time to go on to the applications, but it allows us to study zero modes in certain situations. Okay, so thank you for your patience. Sorry I ran out of time there at the end.
Thank you very much. There are questions?
There's one thing that confuses me a bit, and clearly it's because I misunderstood what's happening. So you know, if say on the circle, you take a measurable function invariant under an irrational rotation, by ergodic theory, that's a constant function, right?
Mm-hmm.
And here you seem to define your things as invariant under some sort of irrational rotation, and I don't see why they aren't just constants by this same general.
On circles, but we're working on the whole of the plane.
Basically, at the they'll be constant on some sort of transversal.
They're constant, well, the functions on our orbit space, if we have an irrational rotation, are constants on those circles. They have a radial dependence. That is the freedom you've got. You've actually reduced essentially to a one-dimensional problem.
Okay, so
Yeah, so you've got essential freedom in that direction, but in that direction, as you say, you're locked down to a constant. Well, there is an extra dimension. That's the key here. And for the line bundles, it's not constant going around. It's it's like e to the I theta or e to the 2I theta, e to the minus k 26 theta or something. You've got a phase as you go around as well. Yeah. So in the irrational case, you are reducing to a collection of one-dimensional problems in effect, but this is indexed by a much bigger set, or much bigger. I mean, it's countable in both cases, but rather than just having just the integers indexing your problem, you've actually got this multiples of kappa 1 and kappa 2, so it's this dense set of parameters that index the problem. So you've got more problems that are somehow simpler. Yeah. And if you take a rational case, then you've got a sector. You've got freedom of providing the information for the function on a sector, and then that sector gets copied around possibly with some phase as you go around the circle. So it's a two-dimensional problem in that case, and the parameter space, instead of being dense over the whole of R, it's just some fraction, then all the integer multiples of that fraction. So there is, it's going back to what you said, it's a very different problem for a very small change of parameter, but somehow this sort of glosses over that or sits above it.
And do you see appearance of sort of the properties of what happens there, say the Diophantine character of these irrational rotations, or it doesn't really matter? It's just
I'm not seeing anything to do with that.
Any more questions?
Is there a condition at infinity for the magnetic field right at the beginning when you lift it up to the sphere?
Right. In order to be parallel to x, it actually forces it to have sensible behavior at infinity. So yeah, because it has this some sort of invariance along the field lines, and the field line, one of them goes through infinity, you can actually get it regularity properties at infinity. So in effect, the condition that it's parallel to x forces the magnetic field to be a pullback of something from R3. So it doesn't necessarily, it goes to zero at infinity, but it goes to zero in a very nice way. It has complete asymptotics that you can develop from what you're pulling back from R3. The North Pole has a full expansion, and that will give a corresponding asymptotic expansion for the field at infinity. Yeah, so there is something sort of buried in that parallel it forces your hand there.
Please.
So at the beginning of your talk, when you defined the spectral flow, I think you got a question on that, which is, are there any concrete examples of magnetic fields for which lambda n prime can be zero? So
Okay.
some sort of quadratic or even cubic.
I wouldn't know about cubic. Concrete, not quite so much. But what is certainly the case, you can get situations where you have a field, an eigenvalue goes down and then back up again. And then there are other situations where it misses completely. So if you take a parameter variation between those two situations, there must be a situation where it just touches. So in that sense, you can argue that there must be cases where the eigenvalue curves just touch. To construct an explicit example, I'm not so sure. That's a bit more subtle, but yeah, they exist. You can't assume that you can just avoid them. You need to deal with them somehow.
And in that case, does the analysis carry through? Or?
Yeah. So the spectral flow is, the definition I gave is the simplistic, the sort of heuristic definition. You need to be more careful. If it touches, what you need to do is develop perturb it a little bit so you have transversal crossings. And then the spectral flow is well defined, and then you need to show that the perturbation you choose doesn't have any overall impact on the answer. So if you perturb one way and you get multiple crossings, or perturb another way and get no crossings, the overall sign spectral flow is unchanged. It's cancellations. So yeah, there's a bit of subtlety there for sure.
Any other questions? Okay, so thanks again.